So in this question, we're asked to calculate the Lyman lines for the transition from the n equals 3 state to the n equals 1 state. And we know that the energy of the states in hydrogen, according to Boyle's model, which actually gives the correct predictions, is equal to minus me to the 4 over 8 epsilon naught squared h squared times 1 on n squared. So what we'll need to do is calculate the energy of the ground state, n equals 1, and the second excited state, n equals 3, and then we can work out the energy difference and get our wavelength. So E1, that's going to be equal to minus me to the 4 over 8 epsilon naught squared h squared times 1 on 1 squared. So substituting in, we've got minus 9.109 times 10 to the minus 31 times 1.602 times 10 to the minus 19 to the power of 4 over 8 times 8.854 times 10 to the minus 12 squared times 6.626 times 10 to the minus 34 squared, and solving that we end up with minus 2.1789 times 10 to the minus 18 joules. So getting it into electron volts by dividing by 1.602 times 10 to the minus 19, we end up with minus 13.6 electron volts. Okay, we're also going to need to know the energy of the second excited state. So we're going to need to know E3, which is equal to minus me to the 4 over 8 epsilon naught squared h squared times 1 on 3 squared, so 1 on 9. Now you can see this is 1/9 of what this was. So this is going to be equal to 1/9 times minus 13.6. So that is equal to minus 1.51 electron volts. Okay, so what we have is we have an electron jumping from the n equals 3 level over the n equals 2 level, that's got nothing to do with it, down to the n equals 1 level. So it's jumping down like this, and as it's doing that, it's releasing a photon. And so the energy of that photon is equal to hf, and it's equal to the difference in the energy between these two levels. And because this is frequency, which is equal to c over lambda, we've got hc over lambda. So we can write this as lambda is equal to hc over delta E, which is equal to hc over the absolute value of E1 minus the absolute value of E3. And so substituting in, this is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over, now this energy needs to be in joules, so we'll do 13.6 minus 1.51. That's the absolute value of these in electron volts, and then to convert it to joules, we divide by we multiply by 1.602 times 10 to the minus 19. And solving that, we end up with 102.6 nanometers. And now for part B, we're asked from the third excited state down to n equals 1, so from n equals 4 to n equals 1. So this is almost the same thing, except that we'll have E4 here. So we'll end up with lambda is equal to hc over E1 minus E4. And we can see that E4 is going to be equal to, like here, 1 over 16 times E1. So we can write this as hc over, this will be E1 minus 1 over 16 E1, absolute values of these things. And so let's substitute in now. We've got 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over E1, which was equal to 13.6 minus 13.6 over 16. And these are both in electron volts, so we multiply by 1.602 times 10 to the minus 19. And then we can solve that on the calculator, and we get 9.73 times 10 to the minus 8 meters, which is equal to 97.3 nanometers. Okay, so we've solved part B now. Now part C asks us if 1 over lambda is equal to R times 1 on NF squared minus 1 on NI squared, what's the expression for R? So to answer this one, we can use that delta E is equal to, we're taking the absolute values, so we're going to ignore this negative sign here. So this is equal to me to the 4 over 8 epsilon naught h squared on, that's the final state, minus me to the 4 over 8 epsilon naught h squared on the initial state. And we know that this change in energy is equal to hf, which is hc on lambda. So pulling this out as a common factor, we've got me to the 4 over 8 epsilon naught squared h squared, 1 on nf squared minus 1 on ni squared is equal to hc on lambda, which we just want to move the hc down here. Then we've got the 1 on lambda by itself. So this is equal to 1 on lambda, me to the 4 over 8 epsilon naught squared. Now it's h squared divided by h, so that's h cubed, 1 on h squared divided by h. So we have an extra h on the bottom, and then we've got this c on the bottom as well, and then that's times 1 on nf squared minus 1 on ni squared. So we've run out of space a bit now, but this thing here, this is R, which is our Rydberg constant. And we can substitute in our values that we've got here. And we actually find that the Rydberg constant is equal to 10,973,731 inverse meters. So this has been measured very accurately. And so that is how we actually end up getting our expression for the Rydberg constant.